unravel the mystery behind a very important aspect of organic chemistry, which is alkanol. Now, throughout this class, this is the outline that we'll be following. We'll talk about the introduction, we'll give an introduction into alkanols, we'll talk about the nomenclature, how to name alkanols. Once we're done with how to name alkanols, we'll talk about the classification of alkanols. You hear stuff like primary, secondary, tertiary, you hear stuff like monohydric, trihydric, and polyhydric alkanols. Once we're done, we'll talk about the physical properties of alkanols. We'll use ethanol as an example, and we'll talk about the method of preparation of ethanol. Once we're done with method of preparation, we'll talk about the chemical reactions of ethanol, such as your amphoteric reactions, dehydration, and finally we'll talk about the test for alkanols. So just stick with me till the end of this class. I guarantee that every single important thing under alkanols will be revealed to you before the end of this particular class. So we've heard of alkanols before, but what exactly are alkanols? Now, alkanols, they are compounds that have three basic components. Alkanols are generally compounds that have three basic components. What are the three basic components? They are saturated, plus aliphatic, plus the hydroxy functional group. This is an alkanol. So alkanols, they are saturated in the fact that the bond between carbon to carbon is a single bond. They are aromatic in the fact that they are aliphatic rather, in the fact that they do not have any aromatic system like your benzene system. They do not have it. So that is why we regard them as aliphatic. They do not have any benzene ring. And finally, they have this OH group, which is the most unique feature that helps me to recognize an alkanol. So any compound that is saturated aliphatic and has this OH functional group, automatically that compound becomes an alkanol. That is why we define alkanols as saturated aliphatic compounds that possess the OH functional group or the hydroxy functional group. Keep in mind that alkanols are not the only compound that have this OH functional group. They are not the only compounds. For example, we can even have compounds. The compounds that have this OH group generally fall into a group known as alcohols. So if the alcohol tend to be saturated, for example, saturated and aliphatic, that alcohol is generally known as an alkanol. If the alcohol tends to be unsaturated, that alcohol, if it has a double bond, it can be an alkenol. If the carbon to carbon is a triple bond, it can be an alkynol. Likewise, if it is aromatic, for example, it has a benzene ring, we can typically refer to them as phenols. So alcohols, rather alkanols, are not the only organic compounds that have this OH group. Very important. Compounds that have the OH group, they generally fall into this group known as alcohols. So we can say that alkanols are a group or a subgroup of alkanols. They are the alcohols rather of alcohols. They are the alcohols that are saturated, aliphatic, and have this OH functional group. Very simple. So overall, we have said that alkanols, they are saturated aliphatic compounds that have the OH functional group, and they fall under the general formula, or they have the general formula CnH2n plus 1 OH, or also written as ROOH. Now look at this general formula, CnH2n plus 1 OH. This is oddly similar to CnH2n plus 2. And if you watched our introductory videos, you should know that CnH2n plus 2 is the general formula for alkane. So therefore, alkanols are said to be derived from alkane by replacing a hydrogen in an alkane with a hydroxy group, or by replacing the Ne at the end of alkane with ol. So for example, if this is alkane, if I replace the Ne with ol, I will get alkanol. So let's pick, for example, the first member of the alkane homologous series. We have methane, ANE. If I replace the Ne, I will get the first member of the alkanol homologous series, which is methanol, If I replace, let's pick another member, which is ethane. If I replace the Ne with all, I'll get the second member of the alkanol homologous series, which is ethanol. Now, what is the formula for the molecular formula for methane? The molecular formula for methane is CH4. The molecular formula for ethane is C2H6. If I replace one hydrogen in both of them with OH, what will I get? I will get CH3OH. What will I get on this side? I will get C2H5OH. This is methanol. This is ethanol. So, alkanols are said to be derived from alkanes by replacing the hydrogen, one hydrogen in alkane, with OH, or by replacing the Ne at the end of alkanes with ol. Very simple. Now back to this general formula we gave for alkanes. Back to the general formula we gave for alkanols, rather. We said that alkanols have the general formula CnH2n plus 1 OH. So where n is equals to 1, let's make n is equals to 1. This n here represents the number of carbon atoms. So where n is equals to 1, we have C1 H2 bracket 1 plus 1 OH. What will I have? This will give us C. 2 times 1 gives us 2 plus 1, that's 3, CH3 plus the OH. This is what the first member of the alkanol homologous series known as methanol. I can keep doing it. Let n equals 2. What do I have? We have C2 H2 in bracket 2 plus 1 OH. What do I have? This will give me C2 H. 2 times 2 gives us 4 plus 1. That gives us 5. 5. Then add up your OH, and we have OH. This gives me the second member of the alkanol homologous series known as ethanol. I can also make it n is equals to 3. Let n equals to 3. What do I have? We have C3 H2 in bracket 3 plus 1 OH. This will give C3 H. 3 times 2 gives us 6 plus 1, that's 7. Then add up your OH. OH gives us the third member of the alkanol homologous series, which is known as propanol. So don't forget, the general formula, the functional group in alkanol is the OH functional group, but the general formula is written as CnH2n plus 1 OH or ROH, where your n is typically equal or greater than 1. Very simple. Now that we've talked about the introduction to alkanols, let's now talk about the nomenclature of alkanol. How do you actually name alkanols? Now, the nomenclature of alkanols is very unique. However, like I've said before, nomenclature is an integral aspect of organic chemistry, so much so that there is almost no single homologous series in organic chemistry that you will not be required to name. So please go back and watch our videos under nomenclature of organic compounds. Now from that video, you should be aware that IUPAC nomenclature is simply made up of 3 basic components. What are the 3 basic components for IUPAC nomenclature? We have the prefix plus the parent name plus the suffix. This is equal to the IUPAC nomenclature. What is your suffix? Your suffix simply represents the primary functional group in the organic compound. In this case, we are dealing with alkanol. So our primary functional group becomes our OH functional group, ol. What is the parent name? The parent name simply represents the root name, or it represents the longest continuous carbon chain. So the longest continuous carbon chain represents the parent name. So that is why in organic chemistry, in nomenclature of compounds in organic chemistry, one of the first things you have to do is to count the longest continuous carbon chain. That will give you your parent name. Then your prefix. Your prefix simply represents usually 2 things. Your prefix can represent any branch that is present, any alkyl group or a branch that is present. For example, methyl, ethyl, propyl, and so on. It can also represent any secondary functional group that is present in the organic compound. For example, chloro, secondary functional group. For example, any other functional group that OH should be giving preference under that condition, that will fall under your prefix. So branches like alkyl groups, secondary functional groups like your halogen group, everything falls under your prefix. So if I can determine my prefix, add it up to my parent name, add it up to my suffix, everything will give me the IUPAC nomenclature of the organic compounds. So let's give an instance. For example, I can write different types of organic compounds, different types of alkanols. I can start from CH3, the CH2, I can have OH, I can have CH3, I can have CH2, I can have this is CH3, I can have this is CH3, I can have this is the OH functional group, I can have, let's write a bunch of alkanols on the board. I can have CH3, I can have this is OH, this is CH3, CH3, CH2. I can have, this is CH3, this is CH3, this is CH3, this is CH2, this is CH2, this is this is OH, this is CH2. So let's use these guys as an example. What is the nomenclature of the following compounds? We have A, this is B, C, this is D. Let's name this organic compound. Let's name this alkanol. How do we name the alkanols? Very simple. Number one, the first thing to do is to determine the longest continuous carbon. Determine the longest continuous carbon. If I can determine the longest continuous carbon, I have done at least 50% of the journey into naming of organic compounds. So determine the longest continuous carbon. In this case, this becomes the longest continuous carbon chain. This becomes the longest continuous carbon chain. In this case, this becomes the longest continuous carbon chain. In this case, this becomes the longest continuous carbon chain. In this case, the longest continuous carbon chain, this becomes the longest continuous carbon chain. So the first thing to do is to identify the longest continuous carbon chain. Now, as I've identified the longest continuous carbon chain, it gives me one important component of this formula. And what do you think that important component of the formula will be? It will give me my parent name. So for example, here, I already know what my parent name will be. My parent name, most likely there are two carbon atoms here. So my parent name will give me Et. That becomes my parent name, Et. Count the number of carbon atoms, 1, 2, 3, 4. 4 carbon atoms. The parent name gives us But. Count the number of carbon atoms, 1, 2, 3, 4. So my parent name also gives me But. Count the number of carbon atoms, 1, 2, 3, 4, 5. So my parent name gives me Pent. Very important. So we've determined one important component of this formula, which is the parent name. What is the next thing to do is to number the carbon atoms, beginning from the side that is closest to the functional group. In this case, the functional group is OH. The primary functional group is OH. So we will number from the side that is closest to the OH functional group. So for number, this is the part closest to this OH functional group. So this becomes my carbon 1, this becomes my carbon 2. If we should number, this is the part closest to the OH functional group. So this becomes my carbon 1, this becomes my carbon 2, my carbon 3, this becomes my carbon 4. If we should number, this is the one to meet the OH functional group. So obviously, this is the part closest to the OH functional group. So if we should number, this will give me 1, 2, 3, and finally 4. For the last one, same thing. Number from the side closest to the OH functional group. If we number, this will give me my carbon atom 1, 2, 3, 4, finally 5. Very important. So the first thing we did was to determine our longest continuous carbon chain. The second thing we did was to number from the side closest to the functional group, OH functional group. Then once we have numbered from the side closest to a functional group, what do we need? the next thing to do is to check for your prefix and your suffix. We already know what our suffix will be. Like we said, our suffix is the primary functional group. So our suffix will always be all, in this case, all. Our prefix is the major concern. Our prefix, we said, can be a branch. Our prefix, we said, can also be a secondary functional group. In the compounds we have on the board, there's no secondary functional group, but some of the compounds do have branches. So, for example, this one does not have any branch. So, for the prefix becomes 0. We have our parent name. Our parent name is et. Our suffix is o. So, if I combine it together, what becomes A? A equals ethanol. The next one is for B. What about B? We said there's a branch. This branch here is a methyl group. So if we combine it, prefix plus parent name plus suffix will give us the IUPAC nomenclature for B. So what do you think it will be? The prefix, we have it, is the branch. Methyl. Methyl is at where? Carbon 2. So this will be 2-methyl. Prefix plus parent. What is the parent name? Parent name is 1, 2, 3, 4. That's but. Why the suffix is all? Combine it together. 2-methyl butan. No. Simple. What about C? What is the prefix for C? There's a branch. Same thing. The branch is at carbon 2. So this is 2-methyl. So 2-methyl. 1, 2, 3, 4, butan, no. So it is basically the same thing with the other compound. What about D? Check. For the prefix, we have 2 branches. We have a methyl group, 2-methyl. We also have another methyl group at carbon 4-methyl. So rather, this is 4-methyl. 4-methyl. So since there are 2 methyl group, that's dimethyl. So this becomes 2,2-dimethyl. What about the parent name? 1, 2, 3, 4, 5. We established that the parent name is pent. So this is pent. What about the suffix? The suffix is O. So this is pentanol. Very simple. So for the first compound we have, the IUPAC nomenclature becomes ethanol. The second compound is 2-methyl butanol. The third compound is 2-methyl butanol as well. Finally, the fourth compound is 2,2-dimethyl pentanol. Very simple. So please don't forget, when you are naming an organic compound, you must remember this equation. The prefix plus the parent name plus the suffix will give you the IUPAC nomenclature, where your suffix is the primary functional group in the organic compound. Your parent name is the longest continuous carbon chain in the organic compound, and your prefix can either be the secondary functional group, or your prefix can be the alkyl group, the branch that is present in that particular organic compound. Very simple. So now that we have established the nomenclature of organic compounds, now that we know how to name alkanols, the next thing we'll talk about is the classification of alkanols. So since we understand how to name alkanols, the next thing we need to talk about is the classification of alkanols. Now, alkanols, very important, have a unique classification. Alkanols can be classified into 3 groups. Alkanols can be classified into 3 groups. How? Based on the number of hydroxy groups that are present. So based on the number of OH groups that are present, we can have 3 different types of alkanols. We can have monohydric alkanols. We can have dihydric alkanols. And we can have polyhydric alkanols. Monohydric alkanols are simply alkanols that have 1 OH functional group per molecule. So if I look at the organic compound and I discover that that organic compound only has just 1 OH group, that organic compound is definitely a monohydric alkanol, most likely monohydric alkanol. But if the alkanol has 2 OH groups per molecule, it is a dihydric alkanol. If it has more than 2, it is polyhydric. So 3, for example, can be trihydric, 4, for example, can be tetrahydric, and so on. But overall, 1 OH functional group, it is monohydric. 2 OH functional group, it is dihydric. OH functional group, it is polyhydric. Now, our monohydric alkanols can be further divided into two. We can further divide our monohydric alkanols into three, rather, based on the relative position. Based on the relative position of the OH group. What do I mean? Based on the number of alkyl groups that are directly attached to the carbon that has the OH group, we can classify monohydric alkanols into three. We can have primary alkanols, we can have secondary alkanols, we can also have tertiary alkanols. So based on the number of carbon atoms in alkanols, we can have three major types of alkanols. We can have monohydric alkanols, we can have dihydric, we can have polyhydric. Monohydric, we said they have one OH functional group. Dihydric, we said they have two OH functional group. Polyhydric, we said they have three OH functional group. Then we said monohydric can be classified into three based on the number of alkyl groups that are directly attached to the carbon with the OH group. We can have primary, secondary, tertiary. What are primary, secondary, and tertiary alkanol? What are primary, secondary, and tertiary alkanol? A primary alkanol is simply an alkanol in which only one alkyl group is directly attached to the carbon with the OH. A secondary alkanol is simply an alkanol in which two alkyl groups are directly attached to the carbon having the OH functional group. A tertiary alkanol is an alkanol in which three alkyl groups are directly attached to the carbon atom that carries the OH functional group. What do I mean? Let's assume this is the carbon atom with the OH functional group. Let me use red. So this is the carbon atom with the OH functional group. This is the carbon atom with the OH functional group. This is the carbon atom with the OH functional group. So let's give this guy an OH functional group. This is OH. This is OH. This is our hydroxy functional group. So I want to show you what I meant by the definition I gave you for primary, secondary, and tertiary alkanols. So these are carbon atoms, three carbon atoms. Each carbon atom has one OH functional group. Now obviously this carbon atom has to bind in three other places. It needs three other substituents. Now for monohydric alkanol, there's only one alkyl group that is directly attached. Just one alkyl group that is directly attached to this carbon carrying the OH. So these two other places can take hydrogen atoms. So therefore, I can say that the general formula for monohydric alkanols will be, this will be ROCH2OH to represent monohydric alkanols. So monohydric alkanols will fall into this general formula. So once I look at the organic compound and I observe that only one alkyl group is directly attached to the compound that carries this, to the carbon atom that bears this OH functional group, that particular alkanol becomes a primary alkanol. For secondary alkanols, I have two alkyl groups directly attached. So obviously here becomes a hydrogen. I have two alkyl groups directly attached to this carbon that bears the OH functional group. So I can say that for secondary alkanols, they will generally fall into the general formula R2CHOH. For tertiary, they have three alkyl groups, 1, 2, 3, that are directly attached to the carbon that bears the OH functional group. So we can say that for tertiary alkanols, they will generally fall into the general formula R3COH. So alkanols that have just one alkyl group directly attached, just one alkyl group directly attached to the carbon atom that has the OH functional group, that alkanol becomes a primary alkanol. If it has two alkyl groups directly attached, it becomes secondary alkanol. If it has three alkyl groups, it becomes a tertiary alkanol. Now let me see if you actually understand what I just explained. I will give a bunch of structures on the board and I will ask you to identify which of them is a primary, which of them is a secondary, which of them is a tertiary alkanol. So let's go. For instance, I have CH3, I have C, this is H, H, this is OH, I can have C. This is CH3. I can have C. This is OH. This is H. This is H. I can have CH3. I can have C. This is CH3. This is CH3. This is OH. I can have CH3. I can have C. This is CH3. This is CH. I can have C. This is OH. This is CH3. This is H. I can have CH3. This is CH3. This is H. This is OH. So let's stick with this one. Let me bring it down a little bit. CH3. This is CH3. OH. And this is H. So look at these organic compounds. This is A, B, C, this is D, and this is E. So look at these organic compounds. Pause the video and identify which of them is primary, secondary, and tertiary alkanol. Don't forget what we just said. For primary, we have one alkyl group directly attached to the carbon with the OH. Secondary, we have 2. Tertiary, we have 3. Very simple. First of all, let's name them. Or rather, let's identify before we name. So, if you look at this compound, or look at the carbon atom, the first thing you have to do is to look at the carbon atom, identify the carbon atom that is carrying the OH functional group. So, look at the carbon atom that has the OH functional group. So, if you look at the carbon atom with the OH functional group, how many alkyl groups are directly attached? 1, 2, 3. So, because 3 alkyl groups are directly attached to this carbon with the OH, automatically this compound will become a tertiary alkanol because it has 3 alkyl groups. Look at this compound. How many alkyl groups are, look at the carbon atom with the OH. How many alkyl groups do we have attached to this carbon directly? It is just 1 alkyl group. So automatically this becomes a primary alkanol. Look at this compound. This is the carbon that is carrying the OH functional group. How many alkyl groups are directly attached to this carbon? It is just 2 alkyl groups directly attached to this carbon. So automatically, this becomes a secondary alkanol. Look at this one as well. Look at this one as well. There is just 1 alkyl group. Rather, look at the carbon atom with the OH functional group. There's 2 alkyl groups directly attached to this carbon with the OH functional group. So automatically, this compound becomes a secondary alkanol. I can even decide to draw a similar structure. Let's call this F. I can have CH3. I can have C. This is CH3. This is CH. I can have C. This is CH3. This is CH. I can have, let's say, C. This is H. This is H. And this is OH, for instance. So look at this compound. Tell me if it is primary, secondary, or tertiary. Obviously, this compound will be a primary alkanol. Why? Because this is the carbon with the OH functional group. There's only 1 alkyl group directly attached. So this also is a primary alkanol. But I want to show you something. Look at this compound. Is this compound a primary, secondary, tertiary alkanol? By definition, a primary alkanol, first of all, this compound is methanol. By definition, a primary alkanol is an alkanol that has 1 alkyl group directly attached. But this compound does not have any alkyl group directly attached to this carbon atom with the OH functional group. So because of that, it should not be represented as either primary, secondary, or tertiary. But to an extent, methanol can still be considered as a primary alkanol because it can still display the chemical reactions of primary alkanol. We'll do it when we talk about the oxidation reaction of alkanol. When we oxidize primary alkanols completely, it gives us alkanoic acid, of which methanol can also do that. So based on reaction, we can consider methanol as a primary alkanol, although it will not be a true primary alkanol. Now, what is the name of this compound? Let's name the compounds we have on the board. So if we name this compound, obviously this is 2 carbon atoms. This is ethanol. If I had to name this compound, this is carbon 1, carbon 2, carbon 3. So this is 2-methyl propanol, propan 1O. or you say propanol. If we are to name rather propan-2-ol, because it is at carbon 2, this is carbon 1, carbon 2, carbon 3. What about this guy? 1, 2, 3, 4. So that's both. There is a methyl group at carbon 3, that's 3 methyl. The OH group is at carbon 2, that's 2O. So this has to be 3 methyl, butan 2O. What about this one? This is our longest continuous carbon, obviously. There is no branch, and the all group is at carbon 2. This is carbon 1, carbon 2, and carbon 3. So this becomes propan 2O. What about this? Finally, our longest continuous carbon, this is our longest continuous carbon. So if we number from the side that is closest to the OH, this carbon 1, carbon 2, carbon 3, and carbon 4. So we know that because it is 4, the parent name has to be both. Our branch is at carbon 3, this is our branch. This is 3 methyl. The all group is at carbon 1, that's 1O. So this is 3 methyl, butan, 1-ol. Simple. So we've identified which of them is primary, secondary, tertiary. We've also named them as well. Now from the names, we can also know if the compound is primary, secondary, or tertiary. What do I mean? Now generally, if the OH functional group is at carbon 1, for example, 1-ol or ol, for example, propanol, propan 1-ol, ethanol, butanol, butan 1-ol, continuously. If the OH group is at carbon 1, that particular alkanol is a primary alkanol. So for example, ethanol, this is a primary alkanol. So if the OH group is at carbon 1, regardless of whether it has a branch or not, if the OH group is at carbon 1, it is a primary alkanol. For example, 3 methyl butan 1-ol. Provided the OH group is at carbon 1, it is a primary alkanol. Also compare. What about for secondary and tertiary? If the OH group is not at carbon 1, then it can either be a primary alkanol or a secondary alkanol. Once that OH group is not at carbon 1, it can either be primary or secondary. Now, if the OH group and the branch are on the same carbon atom, for example, 2 methyl butan 2O, for example, 2 methyl pentan 2O, for example, 2 methyl hexan 2O, the OH group and the alkyl group are on the same carbon atom, that particular alkanol is a tertiary alkanol. So for example, let's see, we have 2 methyl propan 2O, 2 methyl propan 2O. So the OH group and the alkyl group are on the same carbon atom. The OH group and the alkyl group are on the same carbon atom. So for that reason, this alkanol is tertiary. So 2 methyl propan 2O tertiary. But if the alkyl group and the OH group are not on the same carbon atom, if the alkyl group and the OH group are not on the same carbon atom, and remember, your OH group is not at carbon 1, that alkanol is a tertiary alkanol. So for example, we have 2 methyl butan 2O. The alkyl group and the OH group are on different carbon atoms, so that gives us a tertiary alkanol. Now we've talked about the introduction to alkanols. We've talked about the classification of alkanol. So we now know the classes of alkanol. Now what is the next thing we have to talk about? We now talk about the physical properties of alkanols. Now we have two key properties that we have to talk about, because your understanding of these areas is very important. You'll be tested on in your exams. So we have two key areas, two key important properties. We have the boiling point and we have the solubility. Now the boiling point from alkanols and the solubility of alkanols is quite unexpected. And the reason it is unexpected is because alkanols have the ability to form a special type of bond known as hydrogen bond. So if this is one alkanol molecule, this ROH, this alkanol molecule can interact with another alkanol molecule by forming a special type of bond. This bond, we refer to it as a hydrogen bond. Likewise, this same alkanol molecule can also form a bond with water. This type of bond also is hydrogen bond. So this is also a bond. This is also a bond. So for that reason, alkanols display two unique properties when it comes to boiling point and solubility. Alkanols have an unusual high boiling point than their corresponding alkane. They also have a higher solubility in water than their corresponding alkane. Why? Because of their ability to form hydrogen bond with water for the solubility and with other alkanol molecules for the boiling point. So the ability to form hydrogen bond is responsible for the unusual high solubility of alkanols in water and also for the unusual high boiling point. But what are some of the factors that affect the boiling point and the solubility of alkanol? One of these factors is the number of carbon atoms. Now, carbon as a compound is not well known to be soluble. Carbon essentially as a compound, as an element rather, is not quite soluble in water. It's not known for its solubility in water. So the more the number of carbon atoms begins to increase, the lesser the solubility will occur, or the lesser the solubility will begin to happen. So for instance, the lower members of alkanols are generally soluble in water. But as the number of carbon atoms begins to increase, the compound no longer becomes soluble. So higher numbers, up to the point that higher numbers of alkanols are generally not soluble in water. So it is actually the lower members of alkanols that are soluble. So as the number of carbon atoms begins to increase, the solubility of the alkanol begins to reduce, but the boiling point begins to increase. So with respect to number of carbon atoms, we said that solubility will decrease, but boiling point will increase. So as the number of carbon atoms begins to increase, solubility reduces, boiling point increases. What other factor do you think can also affect the boiling point and the solubility? Yes, it can also be affected by the nature of the alkanol, whether it is primary, secondary, or tertiary alkanol. So if this is a primary alkanol, remember for primary alkanol we have R, this is C, we have OH, this is H, this is H. So for secondary alkanols we have R, this is C, this is OH, this is R, this is H. For tertiary we have R, this is C, this is OH, this is R, this is R. It's primary, secondary, tertiary. So for primary alkanol, you can see that the OH group is at the end or beginning of the carbon skeleton. So because of that, the OH group can easily interact with other water molecules and easily interact with other molecules as well. It can easily interact with water molecules, it can easily interact with other alkanol molecules. So because it can easily interact with water molecules, it can form hydrogen bond easily with water, making this compound much more soluble in water. Because it can also easily interact with other alkanol molecules, it can also form hydrogen bond, making the boiling point to increase as well. Compared to tertiary, the three alkyl groups that surround the OH group tend to partially reduce the ability to form hydrogen bonding. So because of that, primary alkanols tend to have a higher boiling point and solubility, compared to secondary and compared to tertiary. So the sequence becomes that the solubility of primary alkanol is much more greater than secondary alkanol and much more greater than tertiary alkanols. Very important. So alkanols, very important. Alkanols, the boiling point of solubility can be affected by the number of carbon atoms. It can also be affected by the nature of the alkanol, if it is primary, secondary, tertiary. For primary, the OH group is at the end or at the beginning, so it can easily interact with other molecules to form hydrogen bond, making it more soluble and making it to have a higher boiling point. But for tertiary, the three alkyl groups tends to block the ability to form hydrogen bond. So because of that, tertiary alkanols tend to be least soluble. Also, they tend to have the lower boiling point. Very important. One other factor can also affect the solubility of alkanols. We've talked about the number of carbon atoms, we've talked about solubility. Also the nature as well. The nature, if it is straight chain or branch chain, it can also affect if the alkanol will have a higher boiling point, and also affect if the alkanol will have a higher solubility. For example, let's look at a straight chain alkanol I can have, for example, CH3, CH2, 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 this is OH. So if I were to name this compound 1, 2, 3, 4, 5, this is pentanol or pentan1O. I can also have the isomeric form of pentanol. I can have CH3, I can have this is CH3, this is CH3, 1, 2, 3, 4, this is CH2OH. If I were to name this compound, this is 2,2-dimethyl propan1O. So if I should compare between these two compounds, which should I expect to have a higher boiling point and a higher solubility? Now, as the length of the hydrocarbon increases, the more linear the compound becomes, the more it easily forms van der Waals forces. So the more linear the compound, the more it easily interacts with other molecules as well, making it easy for the van der Waals force between the molecules to increase. So because of that, the straight chain forms tend to have a higher boiling point compared to the branch chain. The branch chain is much more compact. So because it is much more compact, it readily does not form van der Waals forces. The van der Waals force between this molecule and other alkanol molecules will also tend to reduce as well. So the straight chain forms, the van der Waals forces between their molecules increases, but for the branch chain is more compact. So there's not a lot of surface area for van der Waals forces to occur. So because the straight chain tends to have a higher boiling point because of the higher van der Waals force compared to branch chain, which is much more compact and has a lower degree of van der Waals force. So because of that, it has a lower boiling point. What about the solubility of alkanol? Same thing. As the compound becomes much more linear, the lesser the solubility. So the solubility decreases. As the compound becomes much more compact, much more branch, the solubility increases. So with respect to boiling point and solubility, the more linear the compound, straight chain compound have a higher boiling point but a lesser solubility, while branch chain have a lower boiling point but a higher solubility. So they're like reverses of each other. So keep in mind that we just discussed two key properties of alkanols, which is the boiling point and the solubilities. And we say that alkanols generally tend to have a higher boiling point and a higher solubility because of their ability to form hydrogen bonds. And then this solubility and boiling point can be affected by the number of carbon atoms, can be affected by the nature, whether it is straight chain or branch chain, whether it is primary, secondary, or tertiary. Here we say that as the number of carbon atoms increases, the solubility of the alkanol decreases, the boiling point of the alkanol, as the number of carbon atoms increases, the solubility of the alkanol decreases, while the boiling point will increase. So it is a reverse of each other. As for primary, secondary, and tertiary, we say primary alkanol tends to form hydrogen bond much more easily than tertiary alkanols. So because of that, primary alkanols tend to have a higher boiling point, a higher solubility than tertiary alkanols. Likewise, for whether it is straight chain or branch chain, for branch chain it is much more compact. So because branch chain is much more compact compared to straight chain, for straight chain van der Waals forces increases, for branch chain van der Waals forces tend to reduce because of the compact nature. So because of that, straight chain compounds or straight chain alkanols tend to have a higher boiling point but reverse lower solubility compared to branch chain. We'll talk about introduction, nomenclature, classification, talk about physical properties. Now for the chemical properties of alkanol, to better understand chemical properties of alkanol, we'll take ethanol as an example. Now ethanol is one of the oldest organic compound known to man. It is also one of the most important organic compound known to man. As a matter of fact, the most popular use of ethanol is for making alcoholic beverages, where it is the active component that is well recognized for its intoxicating effect. Alkanol generally is the second member, ethanol is the second member of the alkanol homologous series. It has the molecular formula C2H5OH, also written as CH3CH2OH. This is ethanol. Now let's quickly talk about the method of preparation of ethanol. So how can I prepare ethanol in the lab or even in the industry? Now I can prepare ethanol in three major ways. I can prepare ethanol from ethane. Now keep in mind, remember our video on introduction to organic chemistry. We said that one important feature of a homologous series is that they share similar general method of preparation. So I can also apply these methods to other members of the Alkanols homologous series, and I'll just tweak a little bit of arrangement, and I can get the other members of the Alkanols homologous series. So they tend to share similar general method of preparation. So if I want to prepare ethanol, I can prepare it from 18, meaning that other alkanols, I can also prepare them from alkene. So if, for instance, or for example, if I want to prepare propanol, I don't use 18. If I want to prepare propanol, I have to use propene. So similar general method of preparation. So back to what we're saying. One method I can use to prepare alkanol is from 18. Now, bulk of the 18 is usually gotten as a byproduct from the cracking of petroleum fractions. Now, the formation of ethanol from 18 typically involves two processes, two events, or two stages. So, ethanol is equals to acidification plus hydration. Now, I'm going to say something that I want you to keep it in mind because we will still come back to this. Ethanol, H2SO4, and water, they all share a very close relationship with each other. These four components, ethanol, ethene, water, and H2SO4, they share a very important relationship with each other, such that ethene can be converted to ethanol, ethanol can be converted to ethene, both in the presence of H2SO4 and water. It just depends. So they share a very close relationship with each other, and I will come back to this as we proceed. So back to what I'm saying. The preparation of ethanol from ethene involves two important stages. We have acidification and we have hydration. What am I referring to? First of all, the ethene C2H5, it is first reacted with H2SO4, that's acidification, plus H2SO4. Once you react with H2SO4, what do I form? It will give us C2H. Remember that ethene has a double bond, C. So if I break one of this bond, one comes to this side, the other comes to this side, and H2SO4 simply is made up of H plus and HSO4 minus. So H plus comes to one carbon, HSO4 goes to the other carbon. What do I have? I will have C2. This is supposed to be C2H4. I will have C2H5 HSO4. This is known as ethyl hydrogen tetraoxosulfate 6. Ethyl hydrogen tetraoxosulfate 6. I form this compound. Now this is an intermediate product. It is not the final product. Now I can also react this particular compound. I will react it with water, which brings us to the second process, hydration. Once I react it with water, C2H5 HSO4 plus H2O. Once I react it with water, what do I have? Very simple. Look at this C2H4. Look at this C2H5 HSO4. This HSO4 just needs one hydrogen atom to form back H2SO4. So where do you think you take the hydrogen atom from? Take it from water, obviously. So if water gives one hydrogen atom to this, what do I form? I will form plus H2SO4. H2SO4 becomes complete. Remove this. What will I be left with here on this side? I'll be left with C2H5. So write it C2H5. If I remove one hydrogen from here, what will I be left with? OH. So add the OH to C2H5. This becomes C2H5OH. This is ethanol. So I can prepare ethanol, number one, from ethene, where ethene will be reacted with H2SO4 to form ethyl hydrogen tetraoxosulfate 6, which will be hydrated with water to form ethanol. I can use this method of preparation. This is from ethene. Which other method can I also use to prepare ethanol? I can also prepare ethanol from haloalkane. So like I said, because alkanols we share similar general method of preparation, I just need to change a little bit of things and I can form any member of the alkanol homologous series that I want to form. So I can prepare it from a haloalkane by reacting a haloalkane with sodium hydroxide. So if I have, for example, ROX, and I react it with a base, sodium hydroxide, what do I form? RO picks this OH. Remember, your sodium hydroxide is Na plus OH minus. So your OH goes with this, and we form ROH, which is alkanol. Then X goes with Na, I'll form NaX. So for example, this time around I want to form ethanol. So let's react this compound with, let's say, CH3 or C2H5X. Let X be Cl plus NaOH. What do I form? This is chloroethane. So let's see, what do I form? Very simple. Your OH picks your C2H5. As it picks, what do I have? I will have C2H5OH. Your Na goes with your Cl, and we form NaCl. I can also apply the same general method. All I need to do is to just be increasing the number of alkyl groups here. So if I want to prepare the third member of the alkanol homologous series, for instance, I can use C3H7Cl. This is chloropropane reacting with NaOH. What do I form? Same thing. Your C3H7 picks the OH from here. I'll form C3H7OH. Your Cl goes with your Na. I will form NaCl. So this is ethanol. This is propanol. So I can prepare ethanol from ethene. I can prepare it from a haloalkane. What is that haloalkane? Chloroethane. I can also prepare alkanols from fermentation. Ethanol specifically from fermentation. Now, fermentation is the oldest method used to prepare ethanol. And by definition, fermentation reaction or fermentation is simply the process by which a carbohydrate is broken down by enzymatic action. So if I take a carbohydrate, I break down this carbohydrate in the presence of enzymes, converting this carbohydrate into ethanol plus CO2. That process essentially is what we refer to as fermentation. So it is the enzymatic breakdown of carbohydrates to form ethanol and liberate CO2. Now, on an industrial scale, the carbohydrate we use is typically starch. So we take starchy food, we crush them, and then we obtain the liquid. So the liquid that we have essentially is a liquid that is rich in starch. So because I'm obtaining ethanol from starch, I first need to break down this ethanol in a particular sequence. Because I'm obtaining ethanol from starch, I first have to break down this starch in a particular sequence before I get ethanol. So how do I do that? Very simple. The first thing I'll add is partially germinated barley. Partially germinated barley contains the enzyme known as diathase. Why is diathase important? Because diathase is an enzyme that helps to break down starch. So what is the general formula for starch? We have C6H5H10O5 in bracket N. It will be broken down. This is starch. It will be broken down by the enzyme diathase, and when broken down, it will give us C12H22O11. This is known as maltose. This is starch. So the first thing we add is partially germinated barley, which contains the enzyme diathase. Diathase will act on starch, break down this starch to maltose. Now we need to break down this starch to maltose, break down this maltose. So what do? We add yeast. Yeast contains two important enzymes. What are the two important enzymes in yeast? It contains the enzyme maltase, which we need. It also contains another enzyme known as zymase, which we also need. So remember C12H22O11, this is maltose. It will be acted upon by the enzyme maltase, and when maltase acts on this enzyme, it will break down maltose to C6H12O6. I'm sure you know this one. This is known as glucose. Now we have glucose. We can finally convert this glucose all the way to ethanol. Glucose is C6H12O6. This time around, the second enzyme in yeast we appear, zymase. So zymase is the enzyme that does the most important process of fermentation, converting glucose, this is glucose, to ethanol, C2H5OH, and liberate carboxylic CO2. Very important. Very important. So this is the most important process that is involved in fermentation. The conversion of glucose into ethanol and CO2. So like I said, I can prepare ethanol for fermentation. I would say fermentation is the enzymatic breakdown of carbohydrate into ethanol with the liberation of carboxylic as a byproduct. I would say the first thing to do is to add partially germinated barley, also called malt. It contains this enzyme diastase. Diastase act on starch, break down starch to maltose. Yeast will then be added. Yeast contains two enzymes, maltase and zymase. Maltase will act on maltose, break down the maltose to give us glucose. Then finally, the second enzyme from yeast, which is zymase, will act on the glucose, finally breaking down the glucose to give us ethanol and liberate CO2. So I can obtain it from this process. Now, this ethanol that is obtained from fermentation, this ethanol is typically impure. Usually, this ethanol has a purity of about 95% or 95.5%. Now, this ethanol that is impure, I can also increase the purity of ethanol by fractional distillation. So if I increase the purity of ethanol, I can increase it to a percentage of, let's say, 99.5%. Ethanol of 95.5% is known as rectified spirit, while ethanol of 99.5% is known as absolute ethanol. So I can further increase the purity of ethanol by fractional distillation with a dehydrant. The dehydrant typically used is calcium oxide. So I've talked about the preparation of ethanol from fermentation. The next one and the final method of preparation of ethanol is for molasses. What is molasses? Molasses are simply syrupy liquids that are gotten from the crystallization of sugar. So during the process of manufacture of sugar by crystallization, there is usually a syrupy liquid that is obtained. That syrupy liquid is what we call molasses. So the syrupy liquid molasses is very rich in sucrose. So I can convert the sucrose to ethanol by adding the enzyme yeast. So this is sucrose, C12H22O11. This is sucrose. I can break this sucrose to glucose. That's the first step. I can break this sucrose to glucose. This is C6H12O6. I'm going to add yeast in this process. Why? Because yeast is needed to supply two critical enzymes. We've met one of the critical enzymes before, but this enzyme here is known as invertase. Once I break down sucrose, what do I have? I will have C6H12O6 plus C6H12O6. These two compounds are not the same, despite the fact they have the same molecular formula. This is glucose. This is fructose. So think about it. If I combine glucose plus fructose, it gives me sucrose. So if I'm going back, the inverse is known as inversion. So this reaction where I'm breaking down sucrose to glucose and fructose, we call it inversion. That is why the enzyme involved here is called invertase. So don't forget, glucose plus fructose gives us sucrose. So if I'm going back, that is the inverse. So the process is called inversion and the enzyme involved is called invertase. Once I have this glucose, the second enzyme in yeast, which we've already met, we call it zymase. Zymase will act on glucose, break it down to 6H12O6. Break it down to C2H5OH plus CO2, ethanol in the process. Very simple. So these are the four basic methods used to prepare ethanol: from ethene, from halogenation, from haloalkane, from fermentation, and finally from yeast. Now let's talk about the chemical reactions. Let's talk about the chemical reactions of alkanol. The first one is amphoteric reactions. Now, I want to say makes a point very clear, so please try as much as possible to pay attention. Now, alkanols are not acidic. Alkanols are not basic. But why am I using this word amphoteric reactions? Now, despite the fact that alkanols are not acidic and they are not basic, or rather the best way to put it is they are not strong enough to be considered acids, neither are they strong enough to be considered base. But to an extent, they can also exhibit some slight acidic properties and some slight basic properties. But like I said, it is not strong enough for us to consider them as acids, neither is it strong enough for us to consider them as base. For example, for you to be considered an acid, you must be able to change the color of litmus paper, turn it red. You must be able to undergo 3 basic types of reactions. You must be able to react with metals to liberate hydrogen. You must be able to react with base to form salt and water. You must be able to react with carbonate, which is the most important. You must be able to react with carbonate to liberate CO2. Now, alkanols can do the first reaction, react with metals to liberate hydrogen. Alkanols can even do a little bit of second reaction, but they can't carry out the third reaction. So alkanols, they are not strong enough for us to consider them as acids or base, but to an extent, they can still display a little bit of acidic and a little bit of basic character. That is why we are using this word amphoteric reactions. For example, I can have alkanol, this is ROOH. Under certain condition, the alkanol can be broken down. It can act as an acid by donating a proton plus, this is minus. Also, this ROOH under certain condition can act as a base. This is plus OH minus by donating this hydrogen ion, giving away hydrogen ions in solution. So this is a typical acidic reaction. This is a typical basic reaction. But like I said, it is not strong enough for us to consider them as an acid. So let's see. Let's give examples of reactions that might be slightly acidic, or they might fall under basic characters. For example, reaction with electropositive metals. So alkanols have the ability to react with electropositive metals. They have the ability to react with electropositive metals to liberate hydrogen gas. So for instance, I can have, this is ROOH, can react with an electropositive metal Na. What will it give us? Check this Na. All it just needs is this hydrogen. Na will replace this hydrogen from this position, to displace the hydrogen from this position. What do I have? We have RONA plus H2 gas. This is a typical reaction that alkanols have the ability to undergo. So ethanol, for instance, this is C2H5OH. If you react with very electropositive metal like sodium and potassium, what does it form? OH. Na will replace the position of this hydrogen. Na replace the position of this hydrogen. What do I have? We have C2H5ONA. Then remove this hydrogen. What do I have? H2, giving off as hydrogen gas. This is 2, this is 2, this is 2, if we balance the reaction. So this kind of like an acidic behavior in a way, because an acid have the ability to react with metals to liberate hydrogen. And alkanols can do that with very reactive metals like sodium and potassium. Another reaction that alkanols can also carry out, that may be amphoteric in a way, maybe either acidic or basic in a way, is esterification reaction. What is esterification reaction? Esterification reaction is simply the reaction with alkanoic acids and alkanol to form ester. So alkanoic acids are RCOOH plus alkanol is ROH. So these two compounds can react. And when they react, what happens? Very simple. This is a very simple way to identify what happens. So you see this hydrogen. As a matter of fact, you see this OH here. This hydrogen rather, alkanoic acid is an acid. And the definition of an acid is as a substance that has the ability to donate proton hydrogen ion. So in this case, this alkanoic acid will act as a typical acid. Of course, it's an organic acid. This alkanoid here will act as a base, typical base, by releasing hydroxy ion. This will act as a typical acid by releasing hydrogen ion. So essentially what happens is this: the H simply goes with the OH, while every other thing here simply goes with this arrow. So it is a very simple reaction. So ROCOO picks this arrow, and we have arrow. You see what I have? I will have ROCOO arrow. Then plus, what do I have? I will have H2O. This is known as an ester. So the reaction between an alkanoic acid and an alkanol to form ester, we refer to it as esterification. What does this reaction actually remind you of? It kind of reminds you of neutralization reaction. So it further reinforces the point I'm trying to make, that alkanols to an extent can act as an acid, to an extent, very little extent, can also act as a base. So this is homologous to neutralization reaction. And in this reaction, the difference between neutralization reaction and esterification reaction is that esterification reactions are typically reversible. So the reverse of this process, we call it hydrolysis, while the forward reaction, we refer to it as esterification reaction. Another difference between esterification reaction and neutralization reaction is that neutralization reactions typically do not involve enzymes or catalysts, while for esterification reaction, H2SO4 usually supplies hydrogen ions, which act as catalyst for this particular reaction. So the function of H2SO4 in esterification reaction is to act as catalyst. Now, we can also have another reaction that will kind of be acidic or basic, depending on the reaction. We can have the reaction with, let's say, with PCl3 or PCl5. So if ethanol is to react with PCl3 or PCl5, what becomes the product? Very simple. This is C2H5OH, or rather, let's use the general formula as an example. This is ROH plus PCl3. What do I form in this reaction? This is ROH plus PCl5. What do I form in this reaction? Very simple. In this case, the alkanol will be giving away this OH. So remove this OH, and the OH will be replaced by one chlorine. So they'll kind of give up the same major product. This is ROCl. So both of them gives us the same main product, but the byproducts can vary. For example, with PCl3, your byproduct can be H3PO3. If it is PCl5, your byproduct can be HCl plus POCl3. However, our main product in both reactions is the same. That we react with PCl3 and PCl5 to form haloalkane. For instance, our C2H5OH plus PCl3. What do I have as my reaction, or PCl5 in this case? What do I have as my reaction? C2H5 goes with one chlorine from here. What do I have? I have C2H5Cl plus HCl plus POCl3. So these are typical amphoteric reactions of alkanols. So we said that they are not strong enough to be considered as acids, neither are they strong enough to be considered as base, but under certain conditions they can display some acidic characters and some basic characters. The next reaction we'll talk about for alkanols is the dehydration reaction. So alkanols have the ability to be dehydrated in the presence of H2SO4. However, the product obtained from the dehydration of alkanol, using H2SO4 is dependent on the temperature and the relative concentration of acid and alkanol in the reaction. What do I mean? So with H2SO4, I can have two different conditions. The first condition is high temperature As a matter of fact, roughly around 170 to 175 degrees Celsius. And in the presence of excess acid, so excess H2SO4, this is the condition. I can also have another condition where I have low temperature, roughly around 140 degrees Celsius, and this time around, I have excess alkanol. So, what are my products? First of all, alkanol C2H5, ethanol C2H5OH will react with H2SO4 to give us the intermediate product that is always formed, ethyl hydrogen tetraoxosulfate 6. So OH, we take one hydrogen from here to form water. So I will lose one hydrogen minus H2O. What will I be left with as a product? I have C2H5, then HSO4 from here. So C2H5HSO4. Remember, I've lost one water molecule here. Now this is an intermediate product. Remember, we have excess H2SO4, so it can react with more H2SO4. So if we react with more H2SO4, what do I have? C2H5HSO4. We react with more H2SO4. What becomes my product? Now observe, this HSO4 here, it just needs one more hydrogen atom to form H2SO4. So what will happen is that this guy is like that friend that is always egging you on, encouraging you when you are in a fight. So that's exactly what this H2SO4 will do. It will encourage this one to forcefully collect hydrogen from this atom to form H2SO4. So under that condition, what will I form? I will form 2 moles of H2SO4 here. The initial H2SO4 is this one. The other H2SO4 comes from here to forcefully collect one hydrogen from here to form H2SO4. What will I be left with? I'll be left with C2H4. What is C2H4 called? This is ethene. Did I lose any water from this process? No. Very important. So, under high temperature and excess acid, ethanol will be dehydrated to ethene, or you say alkanol will be dehydrated to its respective alkene. So if it is ethanol, we get ethene. If it is propanol, we get propene. If it is butan-1O, we get but1-ene. If it is butan-2O, we get but2-ene, just like that. What about at low temperature and excess acid? You see this reaction at low temperature, the first reaction is the same in both of them, but this second reaction is where it gets different, because in this second reaction, our C2H5HSO4 will react this time around not with acid, but it will react with the excess alkanol C2H5OH. And once it reacts with the second with excess alkanol this time around, what happens? Now there is no H2SO4 to encourage this one. There is no H2SO4 to encourage our HSO4 to forcefully collect hydrogen atoms. So in this case, it will not collect the hydrogen atoms from here. Instead, what will happen is that this compound has an OH group. As a matter of fact, this compound has a hydrogen ion that it can easily give. This compound has a hydrogen ion that it can easily give to H2SO4. So H2SO4 collects the hydrogen ion from here. Once it collects the hydrogen ion, what do I form? I will form plus H2SO4. So HSO4 takes one hydrogen from here. I will have H2SO4. What will I be left with? I'll be left with C2H5, and on this side I'll be left with C2H5O. So combine it together. What do I have? I have C2H5O, and I have C2H5. What is this compound called? This compound is known as ethane. So the product obtained from the dehydration of ethanol, is dependent on the temperature and the relative amount of acid or alkanol that is used in the reaction. So at high temperature, excess acid, the alkanol will be dehydrated to its respective alkene. If it is ethanol, we get ethene. Propanol, we get propene. But at low temperature and excess alkanol, the alkanol will be dehydrated to its respective alkoxy alkane. So if it is ethene, it will be dehydrated to its ethane. Very simple. There is also a question they can ask you here. They can ask you, for instance, under what condition is it necessary to obtain 1 mole of water from 1 mole of ethanol, and the same 1 mole of water but from 2 moles of ethanol? So what becomes the answer under that condition? So check the first condition. Remember, under which condition is it necessary to obtain 1 mole of water from 1 mole of ethanol and 1 mole of water from 2 moles of ethanol? So check this first reaction. 1 mole of ethanol is involved here. Is there any other ethanol in this second reaction? No. So I just have 1 mole of water. How many mole of water do I form from these two reactions? I have 1 mole of water formed here, but there is no mole of water removed. So I just form 1 mole of water, but from 1 mole of ethanol. But check the second reaction. The second reaction involves this and this, because this reaction is also the same here. So I already formed 1 mole of water. Then the second reaction, is there any mole of water that is formed in the second one? No, obviously. What about for H2SO4? I have 1 H2SO4, or rather, I have 1 ethanol from this first reaction, ethanol. Then, do I also have another ethanol here? I have another ethanol here, so 2 moles of ethanol. So I'm forming 1 mole of water from 2 moles of ethanol. So under high temperature excess acid, I will form 1 mole of water from 1 mole of ethanol. Under low temperature excess alkanol, I will form the same 1 mole of water, but from 2 moles of ethanol. Now the final reaction of alkanols that we'll talk about is the oxidation of alkanols. So I can oxidize alkanols using the common oxidizing agents in organic chemistry, which is KMnO4 and K2CR2O7. So if I oxidize alkanol, the product obtained from the oxidation of alkanols, it is largely dependent on the nature of the alkanol, whether it is primary, secondary, tertiary. So for primary alkanols, we have R, this is C, this is OH, this is H, this is H as well. For primary alkanols have 2 oxidizable hydrogen. When we say 2 oxidizable hydrogen, we can remove this hydrogen. We can also add oxygen to this hydrogen. So we have 2 oxidizable hydrogen. So because of that, primary alkanols can be oxidized twice. So I can oxidize it, the first one, using KMnO4. What is the function of an oxidizing agent in this condition? It is to supply oxygen. So if I supply oxygen for this reaction, what happens? Very simple. OH just needs 1 hydrogen to form water. OH just needs 1 hydrogen to form water. So this OH leaves with this hydrogen, it will form water. This is H2O. What will I be left with here? I'll be left with a double bond. So this is R, this is C, this is a double bond. So this oxygen will gracefully occupy this double bond. Then remember, I'm left with 1 hydrogen here. What have I formed? I have formed RCHO. What is RCHO? That is the general formula for alkanol. So when a primary alkanol is oxidized, it will give us alkanol. But hold on, there's also a free oxidizable hydrogen. I can still oxidize this one further. So because of that, I will also oxidize this alkanol. Alkanol can also be oxidized. In this case, the hydrogen is not removed. Instead, oxygen is added to this hydrogen. So what do I have? I will form R, this is C, this is double bond O, this is single bond OH. RCOOH is the general formula for what? The general formula for alkanol. So this is alkanol, rather alkanoic acid, right? Why this is alkanol. So that simply means that when I oxidize a primary alkanol, I'll get an alkanol as an intermediate product, and I'll get the corresponding alkanoic acid as the final product. But what about secondary? Look at secondary. For secondary, we have R, this is C, this is OH, this is R, this is H. I can also oxidize this, but the problem is that this compound has just 1 oxidizable hydrogen. So because of that, this compound can only be oxidized once. So if I oxidize this compound, what will it give us? OH, the same principle applies. OH just leaves with this hydrogen. Remove it, it leaves as water. What will I be having? I'll be left with a double bond here, and oxygen can gracefully occupy that double bond. I'll be having arrow, this is C, double bond O, this is single bond arrow. Simple. What is this compound? This is ROCO arrow. What is this compound called? This is called an alkanol. So whenever I oxidize secondary alkanols, I can only oxidize them once, and their final product is alkanol. For tertiary alkanols, this is arrow, this is arrow, arrow, this is OH, this is arrow, and this is arrow. Look at tertiary alkanols. Is there any free oxidizable hydrogen? No, no free oxidizable hydrogen. So because of that, tertiary alkanols under normal conditions will not be oxidized. But there's a particular condition where tertiary alkanols can be oxidized, but although in that condition, we have to break this compound. But other than that, under normal conditions, tertiary alkanols cannot be oxidized because there is no free oxidizable hydrogen. Now the last thing we're left with, we talked about the introduction, nomenclature, and so on. The next thing we are left with is the test for alkanols. So how can we test for alkanols? Now there are several tests we can use to identify alkanols. Several tests we can use to identify alkanols. What are these tests? The first test is reaction with metals. We've discussed the reaction. The second test we can also use, remember, with metals, alkanols have the ability to liberate hydrogen in the presence of electropositive metals like sodium and potassium. So they can ask you a simple question that will tell you, for instance, sodium metal was introduced into a test tube that contains an unknown organic compound, and a colorless and odorless gas that burns with a pop sound was liberated. They will ask you, what is the name of the colorless and odorless gas? They can ask you, the organic compound is most likely dash. So obviously, the colorless and odorless gas is hydrogen, and the organic compound can either be alkanoic acids, because they can do that as well. It can also be alkanols. So the first test is with metals. The second test is with oxidizing agents, specifically your K2CrO207 or KMNO4. Now, when K2CrO207 is used as an oxidizing agent, and when KMNO4 is used as an oxidizing agent, there will be color changes. KMNO4 is normally purple. So for KMNO4 will be converted from purple to colorless. For K2CrO207, the normal color of K2CrO207 is orange. But after oxidation occurs, it will be converted from green to green, orange to green. So for KMNO4, if the color changes from purple to colorless, it shows that oxidation has occurred. With K2CrO207, it is from orange to green, also showing that oxidation has occurred. Now this is used for a breathalyzer. So if an individual is suspected to be drunk, that individual is made to blow air into a device known as a breathalyzer, which contains KMNO4 or K2CrO207. So if there's a color change, it tells us that this individual is obviously drunk, and the intensity of the color change will help to tell us the degree of alcoholic content of that particular individual. So with KMNO4, with metals, we can test for it. With oxidizing agents like KMNO4, K2CrO2, we can also test for it. Finally, we can test for alkanols using Lucas reagent. Although in this case, we are not exactly testing for alkanols per se. More or less, we are trying to distinguish between primary, secondary, and tertiary alkanols. Lucas reagent is a solution of zinc chloride and concentrated HCl. This is Lucas reagent. So Lucas reagent is a solution of zinc chloride and concentrated HCl. And we differentiate between primary, secondary, tertiary alkanols using Lucas reagent. And how does Lucas reagent differentiate them? It is because primary, secondary, tertiary alkanols usually react with Lucas reagent in different ways. For example, this is primary, this is secondary, this is tertiary. So for primary reaction, for primary alcohol, there is no visible reaction. For secondary alkanols, visible reaction occurs after 5 minutes. Visible reaction occurs after 5 minutes. While for tertiary alkanols, there is immediate cloudiness, immediate reaction. Usually, cloudiness is formed immediately. So for primary alcohol, there is no visible reaction. For secondary alcohol, a cloudy deposit is formed after 5 minutes. A visible reaction occurs after 5 minutes. For tertiary alkanols, there is an immediate visible reaction that occurs. So far, we have discussed every single thing you need to know concerning alkanols. We've talked about the introduction. We said that alkanols actually belong to a general group known as alcohols, just that they are a group of alcohols that have just single bonds, saturated. So they are saturated aliphatic compounds that have the OH functional group. We've talked about the nomenclature. Remember that the IUPAC nomenclature is equal to the prefix plus the suffix plus the parent name. We've talked about the classification where we classify them into monohydric, dihydric, and trihydric based on the number of OH group. And then we say monohydric can also be divided into 3 based on the relative position of the alkyl group with respect to the carbon that carries the OH functional group, where we classify them as primary, secondary, tertiary. We talk about physical properties, boiling point, and solubility, where we say that alkanols can form hydrogen bond with water and also with other molecules as well. So because of that, alkanols tend to have a higher boiling point and a higher solubility than their corresponding alkene. We've talked about ethanol, where we say that it is the most important, it is one of the most important organic compounds known to man. We said that it is the active ingredient in alcoholic beverages. We talked about the preparation from ethene, haloalkane, fermentation, molasses. We've also talked about the chemical reactions, where we say that alkanols to an extent can exhibit a little bit of acidic behavior and a little bit of basic behavior, but it is not strong enough for us to fully consider them as an acid or as a base. Remember the dehydration reaction, the product obtained is dependent on the condition and also the relative amount of acid or base that is used. So at high temperature and in the presence of excess acid, ethanol will be dehydrated to ethene, or alkanol will be dehydrated to its respective alkene. So with this ethanol, we get ethene, propanol, we get propene, butan 1 or we get butan 1 in, butan 2 or we get butan 2 in. For oxidation, we said the product obtained is also dependent, but this time around on the nature of the alkanol, if it is primary, secondary, tertiary. Primary alkanols, we can oxidize them once, we can oxidize them twice, because they have 2 oxidizable hydrogen, and when we oxidize them, the first one, we'll get alkana. If we oxidize them, the second one, we'll get alkanoic acid. So the final product is alkanoic acid. Then for secondary alkanols, we can only oxidize them once because they just have 1 oxidizable hydrogen. So when we oxidize them, we'll get alkanone, not alkana. Then for tertiary alkanol, we cannot oxidize them because they do not have oxidizable hydrogen. But like I said, under specific conditions we can, but we'll have to break the compound under that condition. Then the test for alkanols, we said we can test for them using metals because they can liberate a colorless and odorless gas that burns with a pop sound. The name of that gas is hydrogen. We can identify them using oxidizing agents like K2CrO2O7 and KMnO4 because of this ability of these compounds to change colors. So if K2CrO2O7 oxidizes alkanol, color change will be from orange to green. But for KMnO4, color change will be from purple to colorless. Then finally, Lucas reagent, we said it is used to distinguish between the 3 different types of alcohols, primary, secondary, and tertiary. Where for primary alkanol, there is no visible reaction. For secondary alkanol, a cloudy reaction is obtained after about 5 minutes. And for tertiary alkanol, there's an immediate cloudy reaction that is being formed.